Good evening and welcome everybody. This is Obi-Wan Pez for N Simple X Pachinko. We're going to be hanging out and doing some math tonight. I forgot to turn that light on again. Alright. There we go. Alright, so that's hopefully going to be fairly comfortable. I am not going to be very comfortable because I still don't have a chair. And I need to plug in. There it is. I have about 10 different cords which all terminate in the exact same place. Yeah, it's great. Perfect. 100%. No notes. And presumably I have a pen around here. Ah, right. It is inside of a book. And also, jeez, you'd think I would wait until I'm actually, like, ready to start, but, you know, we don't learn things here. Yeah. Right. Glove. Alright, I need to somehow fix the scaling on this stream because I'm squashed, but I will do that later because I definitely can't do it now. Hope everybody's been having a good week. Been getting used to the lay of the town. Got my bike working again. Can't remember if I said that last time. And yeah, put up a follower milestone since we're really close to 400 followers. Thought I'd just toss it out there. If you have any friends or anybody who you know has any interest in math education, has any interest in some of the games we play here, let them know and have them drop a follow in here. It's not like, you know, having extra followers really doesn't mean much overall, but it's just kind of a fun number. Alright, so we're just going to keep moving up. Let's get a good seat. Put this down over here. Reasonable. And writing tablet. Cool. Alright, so as per prior streams, we are going to be doing a differential equations, ordinary differential equations class at some point. And cool. And this is our current outline as I see it. During meeting 1-ish, we're going to be talking about the basic history of differential equations, verify some solutions, talk about the fact that differential equations have this sort of P versus NP relationship. So if you want to verify a differential equation, it's super easy. It is P complete, and the issue with differential equations is that we have this sort of NP complete nature of them, which is to say that a lot of times what happens is you either can't take the integral of something, or, you know, that's just scrambled up in some weird way that even if it was a like fairly simple derivative that used one of the like more difficult techniques to find the derivative of this thing, of the original function, it wouldn't be at all obvious like what method to use to go backwards. So in some cases that is the case. In other cases, it's just literally impossible to find out what function will give me this function as a derivative. So this is our NP complete nature of many of our DEs. Classification, we're going to talk about the ordinarity, order, linearity, and homogeneity of these functions, or of these equations, which then allows us to classify like what kinds of tools do we then need to use in order to solve each of the different types. So the big ones that we're always going to worry about in a lot of our differential equations classes are going to be like ordinary and linear. And a lot of the other stuff is just sort of nitpicky. Like whether or not it's homogeneous, we'll work out both. But it doesn't take a whole lot of effort to find solutions to a non-homogeneous ordinary differential equation, one linear ordinary differential equation, once you know how to solve a homogeneous ordinary linear differential equation. There we go. All right, and that fourth group there, the solutions to differential equations are typically, solution methods are typically toolkit in nature, which is to say that it's not going to be just like a one and done, you know, this is how we solve, or, I know what I want to say. Let me unanchor this for a sec. Are we not going to do that now? There we go. Right, so our differential equations are the methods of solving the differential equations will be toolkit in nature, where we're talking about like if we want to get at a particular solution, we can get in there, we can do all sorts of cool stuff, but you're not going to just like use the exact same method 100% on something that looks even similar. Typically what happens is we're going to look at something and we're going to say, what are the different methods that I know how to do on differential equations in general? And then when we start looking at new problems, we can say, okay, well, what are the methods you know? What tools do we know that might be able to help, at the very least, move us forward just a little bit? It doesn't have to necessarily solve it 100%. All right. We talk about existence and uniqueness. So how do we know that there is any solution at all? And then how do we also know that the solution we found is the only possible solution? Once we get past that, the second thing that I want to work on, that really it doesn't have to even necessarily be the second day, but the second topic that we're going to be covering, the larger heading is going to be algebraic solution methods. And so, whereas in meeting one, we're kind of talking about all of the individual overview kind of topics, on topic 2, meeting 2, what we're going to do is actually start like working out the algebra for how to solve these. Alright, so we probably would have looked at a couple of examples in topic 1, and in topic 2 we're going to say, okay, so first thing you want to check is, can you just separate the variables to either side? If you can get something with all x's and something with all y's, then we could separate them and then take the integral of both sides, and it clears out all of our derivatives. So there's two kinds of types. One is going to be those which can be solved easily enough via antiderivatives. So this is your Calc 1 stuff. And then Calc 2 stuff is going to be your U sub, trig sub, what's the differential, or integration by parts. Taylor series solutions, etc. So we go into all that stuff. But generally speaking, it's going to be like, okay, well, I've already seen how to do this. We did it a while ago in previous classes, so it won't be too terribly different to anything anybody's ever seen, and we could just kind of breeze through that, I think. Getting some practice, and especially seeing some weird ones that don't look separable, but you can make them separable. That might be somewhat helpful. There's also a couple of other different methods. I think we were looking at maybe Pascal and Euler have particular methods which allow you to substitute something like, okay, well, let u be equal to x over y. And when you do that, oh, now it's separable into like u and v or something like that. I don't know. Or it's going to be first order linear, right? It's going to be super easy, like one of the ones we see below. The second group is going to be exact equations. So these are going to be things like we see here. We have functions of both x and y, which are both attached to individual differentials, so dx and dy, and their sum of those two terms is equal to 0. So in that one, it gets a little weird. We do have to talk about connections to null lines is way later. Where are we? So the exact equations, if we look at them, and they are, in fact, exact, we want to look at the definition and and those that are just given as, here's an exact equation, solve it. And when we start looking at those, it becomes... This is kind of the first time that we start talking about Calculus 3. So, generally speaking, this is vector calculus. And we start saying that, okay, well, there's, two equations here, two separate terms, and essentially if we think of this whole thing as like we took the derivative of something big, and then all of the x derivatives filtered over this way, and all of the y derivatives filtered over that way. That's essentially what we're doing. Not 100%, but pretty much. Alright, so we're using vector calculus in order to figure out what the solutions are for this. And then we're going to go to integration factors. And actually, we can do that one after topographical maps. Okay, and then we're gonna like use this proof to be like, hey, we don't even need necessarily to have like this big complicated thing that is exact equations. We can now find a simpler case which shows up even more often, which is our first order linear differential equations. So so we look at first order linear functions. Are they exact equations? And yeah, they are. But they're just a special case. Hey, Zach. Thank you for your query. It did kind of light a fire under me. So maybe I ought to, you know, start sitting down and actually writing this. Or the more detailed version that will eventually become, yeah, they will eventually become the actual lesson plan, because, you know, this is not it. Yeah, I mean, so am I. I just said kind of the summer. I think I probably said August because I was backing away from Penn. You know, he was pretty certain that he was going to run his complex class like earlier in the summer, June, July maybe, and I didn't want to step on his toes. Especially since, you know, if we run 2 classes at a time and there's even theoretically some overlap in the students, people are going to get really fed up and tired and whatever else. People will get punchy in one class. Or both. Yeah, just kind of the summer. And for anybody who is interested in at least looking at like the book and things like that, we have it here somewhere. Definitely have it on my phone. Yeah. Alright. Copy this. Come back to my actual page. Alright, here we go. Alright, article equals 1008 is William Trench's book on, what is it, it's both? I think it's both. So differential equations with boundary value problems. Yeah, with boundary value problems. There is also one that does not have boundary value problems, at least not explicitly. And that's a little bit pared down, but it's pretty much the same stuff. It's just a little less in depth. Boundary value problems are more in depth. Let's take this and oh well, go like that. Okay, so intuition. Is that... Nope, that's just regular. I don't know if it was special text. Oh, come on now. Boo. Didn't work. How dare. Yeah, I mean, I can also just give you the page forwarded version, which is that one, which will get you to page 83. Elementary differential equations, yeah, I mean, it's the same. Again, that's going to be the basic one. And then with boundary value problems is the second. So, essentially. Man, can't believe it didn't work. Why am I playing with this? We can just look at this one and say, what is this? It's still the exact same, which means that that is not an M translated into a different font. That was a copied mu, probably from Don's channel. Oh. Not threads, pins. Boo. There we go. Mu. Great. Perfect. Alright, so we got, let's say, strip all formatting. Ugh. Never remember what button it is. Remove all formatting. There we go. So we want this as Laura 11. Normal. Alright, cool. That was even dumber because I could just go over here and copy this one. I don't know why I messed around with the other one. Oh, I'm okay, I promise. Fine, I will accept your usage of the product rule. Alright. Mm-hmm. Nice. Yeah. I like the way he organizes things. We always used the Boyson to Prima, and it was far too small and very expensive. And I mean, it didn't need to be big. It was just that, like, if you had questions, there wasn't a whole lot of, like, explanation. It was just very... Yeah. Yes, very expensive. So much so, I was on the, let's see, 4th edition, I think was the one I bought for my undergrad. And when I started teaching it, we moved into the 10th edition. They were still upgrading it and giving it new, new additions and allegedly some edits or something through the different new editions. But De Prima's been dead since the 80s. Like edition 3. Yeah, and I also actually had 4th edition copy of it that I found from the professors. All those old books that I was sorting through. Yep, here's the 3rd edition Rudin that I used as a graduate student. Mathematical Analysis by Grossa and Hedrick, or translated by Hedrick. Volume 1. This is a good one. I've only started, like, really reading it, but it was very much like, here's how to do calculus. And I was like, wow, okay, we're getting into this. This was written... And Grossa wrote it in 1902, and Hedrick translated it in 1904. This is an original edition of this book. Not particularly valuable, but it just looked cool to have all this. And a couple of undergrad, maybe graduate students who wrote their names in it here and there, and like, this is J. Bar Stouffer, dated February 15th, 1908. So I mean, this was used as a brand new textbook by Mr. Stouffer, probably somewhere in Pennsylvania, if I had to guess. I looked up a couple of people that I found their names like scrawled in various books, and they all seem to be, roughly speaking, from Pennsylvania. And the professor was able to source all of these books. He sourced all of these books from, like, estate sales and stuff like that, which, of course, their kids don't want them. That's how I got half of these. This one is Introduction to Fourier Analysis and Generalized Functions by M.J. Lighthill. This is a fun one because it's really, really tiny. Like, that's the whole book. And this is not even a first edition. This is a souvenir copy. So, like, this was given out at a conference or something. It's crazy to me that, like, you know, this is pre-first edition. But yeah, I took a bunch of the books that I had, basically anything that was, you know, anything that said it was, you know, worth a lot of money potentially, I like set it aside. There was that one from von Neumann which I gave back to the son because I was that felt absolutely wrong for it to leave his dad's house and his possession. It's like, nah, you need to hang on to that, especially since he's an engineer. So, like, he said, dude, this is the kind of cool crap that I just love to have on my shelf and just, like, be able to pull it off someday and be like, I got a book from John von Neumann. Like, yep, that's pretty much what I was thinking. Because he was like, I don't want to, you know, go through the hassle of selling it either and whatever. eBay. Yeah. And that's actually one of the other ones that I had. Did I leave it downstairs? I might have left it downstairs. But yeah, I posted it on Discord, and because Penn was just kind of interested in all this stuff, and I was like, oh dude, you've got to see this. I think I probably showed this at some point. But yeah, this is the preface to the 5th edition of... Those initials ought to be familiar. Cambridge University Press, A Course in Pure Mathematics by G.H. Hardy. I was like, again, this is one of those that's like original, 5th edition, 1928, to be used as a textbook at Cambridge. I don't know exactly where he got this, but again, Philadelphia, Pennsylvania is the first like stamp that's actually on here. So I'm gonna need to get some more. Like Frank Niselovich, something like that. I'm gonna guess that he's probably dead. But yeah, just having the name right on there is just kind of like, that's really cool. Oop. Not exactly what I was looking for, but that's still fun. All right. Anyway. Yeah, the only problem with it is the binding completely came off. It was kind of like flapping. Just sheared right off in our travels over to the UK. I was like, oh, it's bound to happen at some point. All right. I did actually look up somebody who was like a former owner of one of these books, and I was thinking about, like, you know, writing a thing to their family and being like, hey, do you want this? Because, like, your father, your grandfather, whoever it is, like, owned this and something, but nothing ever came of it. It's probably just, you know, I didn't have a whole lot of time. Nobody else had a whole lot of time. All right. So, if we talk about first order linear differential equations, we got here. Okay, what's the relationship to exact equations? Then, oh look, we could do an integration factor, and then we can use the product rule to say, like, you know, in theory, that would have come first. Right, so if we have something that's nice, where it's just like, oh look, it's, you know, y times p on this one, or y prime times p plus what ends up being p prime times y, then that's just a product rule, and we can work with that from just like doing Calc 1 stuff. So can at least bring it together and say, this is where this all comes from. And then again, we do integration factor, say generally, we can just take one of our functions. In this case, it's going to be mu of x, and say we want to take mu of x, or, because that's also a thing, it could be mu of y. So it only needs to be of one variable, rather than saying, oh look, it's, you know, a multivariable equation, x mu of x comma y. Okay. So third group, we've got visualization of differential equations. So we want direction fields, those things which are solvable for dy dx, make it fairly easy, and then do some mixed variable stuff. X's and Y's just all over the place. Okay. What else do we have? So we got direction fields. Or slope fields, if you want to call them that. Really? Alright, well, whatever. There it is. B dy dx is equal to a function of x comma y. Right, so generally speaking. Okay. So in addition to direction fields, we also want to talk about stuff that's like autonomous equations. Well, it kind of belongs to the... So we answer the equation. This is going to be that. Dx is exclusively a function of y. And that could be earlier. And with autonomous equations, we use... what are those called? It's just a number line instead of using like a full two-dimensional plane. But there's like a specific term now, I forget what we did. Oh well. In terms of like fairly simple, that also includes stuff like xy equal, or y prime is equal to xy. You know, things that could be separable, maybe they're not separable. We'll do some hard ones like, you know, y prime equals xy plus y squared minus 7 plus cosine x, or something ridiculous. Something that won't be separable at the very least. Don't want anything like immensely difficult. Non-linear is fine, and in fact something that would not be solvable is actually fairly helpful in this particular instance, because then we can start saying, okay, well, if it's going to be you know, this nonlinear differential equation, then it would be convenient to say like, well, we can't find a solution to this, but we can at least get an approximation for it. So I think 4 here, after doing the mixed, we're going to say like roll as role as an approximation engine. And unsolvable can also be a very relative term, because maybe you're just not as advanced as you need to be. Maybe you haven't studied this particular type of problem, whereas, like, I, for instance, have gone through, you know, some unholy number of differential equations classes. Doesn't mean I know how to do all of them, but still. There's a lot of things that I would look at and say, well, this is not solvable, but somebody higher up the chain might be like, well, yeah, you can actually solve it, but it's going to take some doing, or you can reduce it to a different kind, fit it into one of the above toolboxes that we have. Okay, so we get Euler's method. For this, we want to look at it in terms of figuring out, you get your starting point, and then you're going to, like, find the direction field's slope at your current location. Follow that direction field for a specified dx, and then that's your next value that you're going to get for x. And then you repeat the process. So that's Euler. Hoyne method, I think, is finding an average of the slope value at your current location, slope value at your target location, and finding a weighted average. And then following that particular path until you get to wherever you're heading. Might those be helpful? List of nonlinear ordinary differential equations. Oh, yeah. Here's a whole bunch of special cases that everybody can look at. Now, of course, Jacobi has his own. Rayleigh equation. There's a name I haven't heard in a little bit. Possibly of the Rayleigh scattering fame. Lord Rayleigh, yeah. Rayleigh scattering, yep. Excellent. Yep, so Hoyne's method is looking for a weighted average of the slopes between where you currently are and where you're targeting. It's like the x value where you're supposed to be later. It says, like, all right, well, it should be somewhere in between that. So yep, there you go. There's your new value. Backward Euler is very complicated, and I keep explaining it wrong. So maybe I should not. But essentially, you're looking at the slope that you're going to have in the future and bringing it and solving the equation to figure out what the next x value should be. Like, what x value will have that slope between your current and your future value of x. And it's It's a little bit messed up, and again, I keep explaining it wrong, so hopefully that was the correct one. And Vrongekura, which is quite possibly one of the most awesome and at the same time very messed up sorts of ways to find solutions for differential equations. So this one is very similar to Simpson's method from Calc 2, where you're finding the slope at the current x and y value. You trace it forward, and you find the slope at like the final value, which then is different, which gets you a different value. Nope, I'm wrong. Take this value, go halfway, find out where that is. Then take that value, find the slope field there, and then that's gonna, or the slope value there, and then there's a third point up above it. I don't remember how you get that point, and then you find out like where those two things are. Then you get another. There we go. Then you get a fourth point, which is at x plus delta x. Find its slope, and then take a weighted average of all four of them. So it's very similar to Simpson's method from Calc 2. You're finding this weighted average of a whole bunch of stuff and then just shoving it all in together. Okay, ad break's going to start, so I will start that manually. Makes it a little bit easier on everybody. And then we can Leo was predictable this time. Alright, 3 minutes. Stand up, stretch, do all the cool stuff, get some water, because goodness knows we all probably need a little bit more water. See you in 3 minutes, everybody. All right, we're back. So one of the reasons that Rangekoda is so incredibly effective is because it's using that weighted average of 4 different locations, and it ends up converging to well, not converging. They all diverge away from the true answer, but it diverges incredibly slowly. You could see, like, if you wanted to say, like, you know, what's the, I don't know, you could figure out some particular differential equation to solve and then try to find the answer for it at a particular value, and it's going to be accurate to, you know, orders of magnitude more decimal places than all of the other approximations. That being said, it is a bit more intensive to calculate, so I highly recommend just doing it using a computer. Write a small, 8-line program or whatever to do it in MATLAB, and it really is that easy. We also do Octave. Octave is the free version of MATLAB, and Scilab is the French, similar to but legally distinct from MATLAB application, and it works also very nicely. If anyone does have any questions about mathematics, please interrupt me, because I don't want to, just be sitting here talking the entire time. If you have questions. Otherwise, I will definitely fill the silence. I'm a teacher, I'm used to doing that. And Zach's just sitting over there going, mood. Alright. Yep, they all just look at us going, student reviews back. Oh. I have not been to rate my professor in such a long time, because I just gave up on it. I was like, nope. This is just going to hurt my ego. The only people who actually go there have an axe to grind. Ugh. The official ones. Yep, okay. Yeah. We did, our institution participated in the IDEA survey, the YES survey, and, like, I don't know, probably a couple others, but IDEA was the big one. Yep. YES is YESS, and that's more of like an institution-wide thing, which includes, like, the services that are rendered to the students, not just the yep, not just the academics. So hey, as long as they're not used to, like, potentially fire you, and I mean, like, if they're awful because you're an objectively awful teacher, that's one thing, but, like, if they're awful because students just don't like your class, that's, like, what am I supposed to do with that? Yeah. Yeah, like, I did a observation for one of my, being the coordinator for pre-calculus, right? You sit in on all of the adjuncts over some sort of rotational period. Be like, okay, I'll do 3 this year and 3 next year. If an adjunct has been done at all in the last 7, I think, they don't technically need to be done again. Or maybe it's 3. I don't know. Oh, and if they're going for promotion, they have to be done. So, there was a lot of sitting in and taking notes and stuff like that. But this one guy, I sat in on his stuff, and like, he's just a objectively better teacher than me. He doesn't have like the content connection, but he's just way better in terms of getting the students to actually do the thing and making sure that he's circulating around and doing all this other stuff. And it's like, this is the kind of classroom that I'd want to run if I were at all. Yeah. Maybe you meant it for emphasis, in which case I recommend the asterisk. Or my favorite, parentheses TM after. Took it seriously, trademark. Alright. Oops. I mean, not really oops. That's just... Okay. Okay. So, like, here's where it starts getting... here's where it starts getting fun. So, the standard... ODE class that is taught out of the Voice to Prima book or the Trench book typically will go for no, that's fine. Typically we'll start with the background stuff, go through the algebraic solutions, and actually between 1 and 2 they'll do the visualization. So like, how do you graph differential equations? And then they'll come back to doing the numerical methods at the end of algebraic solution methods. And I was like, I don't know. I think if we switch those around a little bit, put all of the visualization and numerical method stuff at the end of that section, I think it'll condense a lot better, and we get, a nice segue to go from how do we graph differential equations into numerical methods, because direction fields are basically just, you drawing a solution on a direction field is basically you're doing Euler's method. You're just saying, okay, I've got a value here that I know what the slope is, so I'm just going to draw some like curve that approximates it. Sensation. Yeah, that's fair. How you doing? So then we've got first order linear systems, and like normally what goes here is we say, okay, we were just doing first order linear differential equations, and then we're going to move to second order linear differential equations, which is a very nice segue to go from first order to second order. It doesn't change a whole lot, except now we're talking about like characteristic equations and all this other stuff. But one of the things that happened was I was talking with, or rather, I was watching the videos of one Pavel Grinfeld. I was watching his partial differential equations stuff from Lemma. So Lemma is a group that does like a summer program for highly advanced Philadelphia area high school students, I think high school students, or undergrad college, and they've gotten to partial differential equations. Like, I mean, it's just ridiculous what these people are into. He's also got a segment on tensor calc. So, like, now he also wrote a book on tensor calculus, which is the tensor calc book that I have been stuck on for years at this point. But he did two partial. Nope. Nope. Don't want that. Right, so this is the first one. Nope, I don't want that. Damn it. It's on the same one. 7.5 hours deep of nothing. Yeah, I actually can't increase it beyond 720, I don't think. And it's just weird, but it's also I'm also squashed, so that's not helping. Let's see. Oh, my bit rate's pretty low. That might be one of the problems. And it's rescaled to, yeah, 720. So I'll probably need to figure all that stuff out. Ow. I need to fix my leg. Hey. Thank you for the followage. Yeah, a bunch of those have been a part of the stream for I don't even know how long at this point. Yep, Stream Elements. Speaking of, I know that Stream Elements was caught up in some sort of weird CEO being a jerk thing. Basically, I just haven't bothered to switch out, and that's on me. But I need to do much more research into what would be better options and things like that. Okay. So anyway, Pavel Grimfeld was doing his partial differential equations class, and he broke for a little bit to just talk about ODEs. And I was like, that's kind of interesting to like go back and make sure that he's doing like a little bit of just-in-time stuff or layering a couple of pieces of information to be like, hey, this is some background you might not know from your prior DE classes, ODE classes. And in doing it, he's spending like, you know, tiny amounts of time, and he went from first-order linear differential equations to first-order linear systems of differential equations, which is normally our Unit 3, like at the end of the course. Instead, Unit 2 is typically second-order differential equations. And I was like, that's kind of interesting. And then he showed like how this looped in a whole bunch of the linear algebra that was, fundamental to that whole section, and something clicked in my head. I was just like, and I went home and I told my spouse, and she was like, yeah, you took an entire class on that. It was called linearity. It was it was the one where you took multivariate calculus, differential equations, and linear algebra all at the same time. Do you remember this? And I was like, yes. This is the class I got a B and a C in. And I had to repeat half of it because I got a D in it when I had mono. But yeah, so it was kind of like, come on, you should have remembered this. And I was like, oh, yep, okay. No, that makes complete sense. And also it makes complete sense why it just clicked. And when I was watching the video and everything just clicked into place, I looked at the clock and I had 15 minutes until I needed to be in class. And I said, F it, I'm swapping the 2 units. And I went to my coordinator and I said, what do you think? And he's like, you're insane. I was like, yep, let's go. So the students did no worse for me swapping all this stuff around. And I told my class, I was like, this is a complete experiment. I have no idea what's going to happen. If you don't want it, then we can get you out and find you somebody else's class, I guess. But I didn't have anybody leave because of that, so that was good. I think. Oh. I spent most of my early morning this morning. Well, I won't say most. After I dropped the kids off, came back, made myself a coffee, and then I had put a layer of beeswax on our butcher block. So we bought this butcher block table. It's probably about 6 feet by 2.5 or something like that. And it's got shelving underneath it. Very nice. All stainless steel underneath. And so this butcher block is absolutely beautiful. The guy who was here beforehand just was like, well, I can't take it back to the States, so do you want it? So we were like, yeah, okay. Purchased it. And so I was like, oh, how do you preserve it? And there's like all this stuff online. You can get oils of, like, you can't use food oil specifically, like vegetable oil, olive oil, and a whole bunch of the other ones will oxidize, and it's potentially toxic. So, don't do that. So I was looking at it like, well, you also, one of the other problems is you can't heat it because it'll cause the wood to crack. And one of our boards went through the wash. So that was how that one like split right up the middle. So you just cannot do that with wooden cutting boards. But this was, way back in the early days when my spouse and I had just moved here, or not here, had just moved to Maryland together, and she was like, well, it's a dishwasher, so you put the dishes in the washer and it washes them. And I was like, that's, you've never owned a dishwasher. That's not quite how it works. So, you know, A, no wood, and B, most dishwashers are not that efficient, so you have to, like, you know, scrape most of the stuff off. And she's like, what's the point of having a dishwasher if I won't wash your dishes? I'm like, I've had a dishwasher for 20 years. Let's just... Her parents were very old school. Her dad was supposed to put in a dishwasher, like, several times, but then kept getting sidetracked onto other projects around the house. So he just never had one. And my mother-in-law just never got her dishwasher. But anyway, yeah, so I was like, well, what can you put on, you know, what can you put on butcher's block in order to, you know, help preserve it and stuff like that. And the consensus was you need food grade mineral oil and, like, really get that in all over the whole thing. I was like, okay, that seems all right. And I just opened up the you know, the under the kitchen sink area, and there was a big bottle of the stuff I was looking at, which is like orange oil furniture polish, and it is not food grade. I was like, oh no, that's not good. That must be what he used. And I had taken a sponge and just, like, run over it real quick with like soap to kind of get up all the other gross stuff that we put on it. Who knows what. Nothing terrible, just, you know, some food ended up on there and whatever. So I took a bunch of stuff up, and I looked, and, like, the cloth that I'd been using was all kind of grungy, but now I'm realizing it was just orange oil. It's fine. So I cleaned it off, and I took beeswax and I heated it up and just kept dabbing inside this bowl, and then just keep going over the whole thing. And the whole thing ended up really tacky. Like, it was just anywhere you touched, it would, like, stick. I'm like, that's not very good. So this morning, I went at it with a, just like a terry cloth towel, and did the whole wax on, wax off thing, and went at it like basically a square inch at a time all the way across the entire thing in order to spread it out nicely, and then went the other way in much bigger circles, and then kept going until it was pretty much just, like, buffed. So now I touched it, and it was like, oh, it's not really sticky. It's just kind of like, you know, there's a coating on here, obviously. So beeswax, man, works pretty nice. Won't say it's my number one choice, but it is all natural and definitely food safe. Okay. So yeah, Pavel Grimfeld did this thing, and I was like, let's do it, and I swapped them. So I'm gonna do it for here too. I'm changing the order up and see how this works. It also means that the linear algebra portion gets put in earlier into the lineup in terms of the objectives, and those students, you know what? That's not what I want. Let's increase this one to 125. Yeah, thank you, Sensation. I should have realized this is an easier solution. Let's just increase the font size. Or increase our view. Anyway, yeah, so now that we put this in this order, this is going to go from first-order linear differential equations to first-order linear systems of differential equations. And what's going to happen is that we go through all of this stuff, we end up in the matrix form of first-order systems at the same time as the linear algebra students who are in differential equations are learning in their linear algebra class how to do row-reduced operations, or row-reduced echelon form. Get everything in that order and try to solve systems. So it's like, well, obviously this would be a much better pairing in order for these students to like get reinforcement across two different subjects, or across two different classes. But I think it also just makes it much easier to work with. Okay, so we work with the matrix form, eigenvalues and eigenvectors, no client's behaviors by inspection. Okay, so when we start looking into first-order linear systems, we get the expanded form, which is just literally, again, it's a system of equations. Yes, they're differential equations, and yes, they typically depend on each other. So this is going to be stuff like our mixed salt problem within two tanks. So you've got a tank that accepts high salt content water, and then you have a well-mixed apparatus, you know, some sort of mixing apparatus, which well mixes the stuff that's in the tank. And then you have a connection which runs to a second tank, which feeds in water from this one and then feeds water back. And it's considered well mixed, you know, instantaneously, which is somewhat ridiculous, but whatever, it's fine. It's close enough. We don't really care all that much. Could also potentially set up an apparatus for that to happen, such that, you know, it will essentially mix it in the right way. I don't know how else to describe it. It's fine. So we could do graphs of first-order systems. I think p-plane 6 does that one. X prime equals and y prime equals, and then you have each of those differential equations operating on each other, or using both variables to get something cool. So the graphs of the first order systems, we can start getting this in, and then we say, okay, based on this, we can also look at, you know, where on this graph do we have what are called nullclines, or like specifically the ones that we care about are the asymptotes and other critical points. So we want actually backwards, right? We want this. Critical points are typically fairly easy to see, and then asymptotes are going to be you know, things that we see which are linear in some place. So we look at it and we say, oh, well, here's a linear function. That also means that the second derivative, right, is going to be 0 for those asymptotes. Alright, and since these are first-order linear systems, it's not going to behave like too unexpectedly. There is going to be a section much later on where it starts talking about first-order non-linear systems, in which case we've got all sorts of weird behaviors. In some places you have like, a spiral sink that's somewhere near like a saddle point, and there's just all sorts of crazy interactions that happen between those two areas. Around a single zero, if you look close enough, it becomes a linear function that's just going through that zero. If you then see something with a higher multiplicity than 1, then locally, again, if you zoom in close enough, it looks like a quadratic or a cubic function, etc., of some kind or another. So you can do a local linearization or a local polynomialization, local, what else could it be? Parameterization? I think that might actually work better. But essentially you're just simplifying the problem and saying, okay, immediately surrounding this particular zero, all you have are those terms which are approaching zero. And if we just focus on those terms, then it's going to look like, whatever kind of polynomial this section is just by itself. Alright, so matrix form. We got the idea of eigenvalues and vectors comes from the null-Klein behavior above. If you're talking about the fact that this is going to be, linearly speaking, well, it is a linear differential equation, so not an issue. If you're talking like around this particular critical point, we end up with a, again, spiral sink, then this is going to tell us that what we have is a complex set of eigenvalues, and then the eigenvectors are going to be, in this case, also non-real. That was maybe a terrible idea. Right, if we get something that looks essentially hyperbolic, right, so around this critical point, everything that's in here is going to go off like that toward those two asymptotes, and like this one's coming in and this one's going out, something like that. If you look at the overall behaviors, then you're going to notice that those eigenvalues are real numbers. They're going okay, they produce eigenvectors, which are the vectors from that critical point in those particular directions, and those are your null-Kleins, which have asymptotic behavior. So you see that, like, essentially the eigenvector is just going to be where the asymptotes are on these saddle points. Don't know what that was. Right, so then we could talk about linearity and independence. So the fundamental set of solutions is going to be based on the eigenvalues, eigenvectors. And then we could talk about, again, existence and uniqueness the same way we do with the first order linear systems. Nope, first order linear equations, where we say, you know, it's going to exist essentially as long as the whole differential equation is continuous. And then how can we tell it's unique? Well, if it's, what is it? If it is continuous and its derivative is continuous or something like that, then it ends up being unique. So there's no other way to get a different solution to the same differential equation. And by that I do mean different fundamental solution rather than different, like, you know, over here you've got a hyperbola like this, but if we go to the opposite section on this graph that's across from its eigenvectors, down here we're going to have something that also is a hyperbola. And then likewise with the sides as well, you end up with these hyperbolic curves. It doesn't mean that those break uniqueness, it's just a different area of the function, which you plug in a specific value as your starting value, it's going to tell you where it goes from there. It's a lot like water flow. So if you can just follow the idea of how water can flow, then a lot of times you'll see where this is all going. I'm cheating. Okay. This is also interesting. Shams puts theory of solutions under linear differential equations. They have the Wronskian linearly independent solutions. linearly differential equations and non-homogeneous equations before they do second order stuff. But then, like, way later, they also have reduction of linear differential equations to systems of first order equations. So they use the nth order equation on this one. It's like halfway through to where they do reduction of order to first order equations. They do like theory of what kind of solutions you have, including the Wronskian. So that's something that I wasn't expecting, actually. Oh, okay. This is the checking to see if you have your all of your differential equations. So in this we discuss whether it is whether given solutions will form a linearly independent set of solutions. Interesting. Okay. So that's our fundamental set of solutions, really. That's where that's going. So this does include fundamental set of solutions. Checking using the Wronskian. So moving to this town, I have done the fundamentally important thing, which is that I have been to something like 8 of the 30 coffee shops at various points and tried to order the same thing and see, like, you know, which one I like best. And so far, the one that is on the way to and from my kid's school on foot is the best. And so yes. Every time we walk, I will stop in there, and sometimes if we drive, I will walk downtown get a coffee and then usually a pastry and walk home. Or, I guess if I drove, then walk back to the car. But either way. It takes us approximately 20 minutes to walk to school. And I'm setting a pretty good pace, so it's probably pretty close to a mile. But oh man, our 7-year-old really complains. He does not like it when Daddy walks to school with us. It's like, oh, why can't we drive? I've got PE today. You're making me run around all day. Can we stop for brownies? Can we stop for ice cream? Something. I need sugar to get up the hill. Okay. Alright, so... No, you follow the same restart numbering? No, okay. Continue previous numbering, then restart numbering at 1. Yes, there we go. I don't know how this works. Yes, a plug. So, those of you who are in the United States, this book will not be out until September, but I highly recommend pre-ordering it. This is Alien Clay by Adrian Tchaikovsky. Absolutely 100% worth the buy. If you at all like science fiction and, you know, like dystopian fighting against the system kind of stuff. Not gonna say much about it apart from that, because it really is worth the experience to go in, much like Outer Wilds, to have as little experience as possible with the novel itself. Tchaikovsky is also the author of Children of Time, and I think there's a trilogy that belongs to. Which my friend living across the street was like, absolutely, you need to buy that book. And I was like, oh yeah, I already got it. It's like, I hadn't started reading it until a couple weeks ago. And I've put it down and not picked it up for a long time too, so. Yay. Children of Time is about a group of humans who are intending on seeding an exoplanet with life from Earth and essentially terraforming it. They will remain frozen on the ship while a hyper-engineered genetic virus will mutate the primates who are on board, and it like specifically targets the primates to basically hack their evolution so that their brains become bigger, and like they develop the ability to have communication, to have speech, to be able to understand things. Eventually the goal is that they will be intelligent enough to break into the human systems, like the technology that's here, and then, as the phrase goes, meet their maker. So they would be able to literally at one point communicate with humans and like ask them, hey, so why are we here? Like, what are we doing? That's the intent. It all goes to hell in the first 10 pages. So I'm not spoiling anything. Alien Clay actually does have a similar kind of like setting, essentially. There's some critical differences that are in there, but The Mandate is a highly authoritarian, fascist religio dictatorship which is akin to like 1500s Catholic Church. You know, the group of people who say this is the way things are, and if you don't like it, we're going to literally torture and murder you. Um, so in this case, basically what they've done is they've taken all of the dissidents and thrown them on ships and sent them out to exoplanets to be prison colonies. And this follows one particular guy in his determination to survive on this prison planet, which basically will kill you. It's just a matter of when and how bad. And instead of like a, you know, nano, or instead of a smart virus trying to kill everybody, it's just the alien life that's already there. Well, no. Children of Time, the virus wasn't killing anybody. It was enhancing evolution. In Alien Clay, there's just like all life on this planet is hostile and will attempt to kill you. So, yay! But yes, I absolutely love it. I'm actually starting to work on a project. Wink, wink, nudge, nudge. Um, which may have something to do with it. But I have no talent in the area in which I have decided to work on this particular project. But nonetheless, it's distracting me, and that's possibly why I haven't done this at all. For UK friends, Alien Clay is out in your local bookshop. And if you don't have it, if you don't find it, I recommend just you can order it directly from his website, I think. He specifically does like supporting local bookshops, and you know, has put out that request that everybody you know, go support your local bookshop and purchase from there instead of online. But he's also done a series of speaking engagements. He is slated to be on the sci-fi panel in Edinburgh, in Scotland, in... I don't remember when exactly it is. Is it Chimera? I think it's Chimera, but it's spelled weird. There's a sci-fi panel that's going to be going on in Edinburgh. That's not it. CYMERA, I believe. Yes, 50 events, 70 plus authors. Chimera 2024 CYMERA. So anybody who is in the UK and likes science fiction, this is an option. And pretty freaking awesome, if you ask me. I don't think I'm going to be able to go. But it does look absolutely... Oh, yeah, it's the end of this month. Never mind. 31st May through 2nd of June. In person and online. So you can go online if you're at all interested. Yeah, so Adrian Tchaikovsky. The other authors include... Trying to see if I know anybody. Probably not. So there were a few other people who were at the sci-fi panel here. in Yorkshire who are like local authors, and so they were tapped to come to this local one. It was just like a panel of 4 authors, and somebody asking questions, and then the audience got a chance to at the end. And then there was a book signing. It was done at a library, which I think is also a very cool thing to do. Una McCormick, if anybody does know, the Star Trek Picard novelizations, or novels of not necessarily the exact same stuff as the show, but that sort of thing. Yeah, I think for the most part, these are people who are much bigger in the UK. I hadn't heard of anyone on this entire list. Of course, I have been really, really bad about not reading books a lot, except the ones that I had to. So once my friend across the street was like, "No, you need to read this," or you should pick up some of this guy's books. It was like day 1, the first full day that we were in the UK, I picked up Alien Clay and 2 mystery books from local authors. And local being Yorkshire, which is big, but nonetheless. They sourced from the entire county. Yeah, this is also interesting. I'm not seeing the other... I'm not seeing stuff from the other authors. Because I thought one of the other authors was supposed to come to this. That was on the panel. Is supposed to be going to the big one. But yeah, I'm not seeing her. Huh. She might have backed out, I guess. Or had something else come up. Feel like... Oh, there. Yeah, there she is. The other one is Lauren Bukes, who recently came out with a book called Bridge. I don't remember exactly what it is, but I think it's like there's like a mental connection between the 2 people, or any 2 people, or something like that. I don't remember exactly what the premise of the book was. I do have a copy of it, but I haven't started it yet. Because I have 2 mystery books and Children of Time to get through. Okay. If anybody does have any questions on math, please let me know. Okay, so topic group 5. You know what, let's do that. Find, replace, just those, cool. Replace all. Thank you. Alright, so 4 second order linear differential equations. Oh, I don't know. But if we're gonna do twice a week, right? The if we're doing 2 hours each, I mean, how long was ours, Zach? I don't even remember. Yeah, because this is just whatever we're gonna talk about, we're gonna talk about. Is it 14 meetings, something like that? 10? 20? Yep, totally. 10. Yeah. Right order of magnitude, I guess. Oh, man. Okay. So, yeah, I would imagine. Yeah. I would imagine it would probably be at least similar. But then, like, I'm also thinking, like, I want to prepare, at the very least, for having more necessary time in order to, like, split things out and have deeper conversations, as certainly happened with our class, the real analysis. But also trying to, you know, find that balance of respecting people's time, being like, yeah, this is not going to be 30 weeks long. That means that here we need oh, nice. Yeah. I mean, at that point, you're like also just doing like expansion to graduate level material, which I do potentially want to throw in there if anyone is interested, but at the same time, like, not if it doesn't develop naturally. Throat singing is badass. Episode 23. Battle of the Eigenvalues. Nice. Okay. Sorry. How we doing? It is now midnight local. We have we do have multiple people who are online. I think probably a few more minutes, and then we might go and raid paleontologizing. Dr. Danny. Yup. Yes, I saw. Danny Highway just reached our, or no, sorry, not Danny Highway. Right, paleontologizing just reached 4 years. I saw he was dressed up in a tux yesterday. I was very impressed. Anduza. There we go. I don't know that he's actually a doctor, but yeah. but he is a paleontologist. He does work in the field, so... actively. Arg. Whatever. So yeah, we might go see Danny and do a paleontologizing. Celebrate his 4-year stream anniversary, and also see what the dinosaurs are up to, because, you know, everybody still has that little bit of them deep inside that's like, man, paleontology. Love dinosaurs. Yeah, stop doing that. All right. So we want general solutions to homogeneous equations, which are going to give us like all the different various types that we're going to get. Okay. Different fundamental solutions, which are going to be not only the types. Well, that could be the connection to eigenvalues and vectors up there. Different fundamental solutions. Okay. Alright, and then we've got to touch on, let's see. Okay, interesting. No, okay. That's particular solutions. I think I've always hyphenated non-homogeneous, but alright. Alright, so one is going to be the non-interacting. Homogeneous and particular function types. So the ones that just come up with something completely different. So we get the, for instance, e to the 2x and e to the 3x, and the non-homogeneous portion is literally anything else, just that is not one of those two things. Nope. Let x equal I pi, yeah. I mean, obviously, right? Gonna have to do it at some point. It's the Zach solution. Alright, so then we've got the so the duplicated ones, which are homogeneous and particular functions, and we've got to somehow come up with these things. So with this, the duplicated ones are going to accelerate or elevate the polynomial that's in front of it by 1 degree, whatever it's going to be. So the homogeneous solution always ends up getting 0, no matter what it is. No matter what's stuck in front of it, right? That's the whole reason it's C1 times this thing plus C2 times that thing. Okay, so our format, we want this to be superscript. Alright, we're gonna remind ourselves that the nth order characteristic is reminiscent of the fundamental theorem of algebra, which is telling us, like, hey, this is how many homogeneous solutions you have. So therefore, if these things show up at any point in your particular solution, we're going to have a bit of a problem. You're just going to have to increase its degree of the polynomial that's sitting in front of it by 1. Until it is no longer overlapping with the homogeneous solution. Okay. So Alright, is there anything else that could possibly be here? Okay. So then we get into our particular solution methods, which realistically this one up here is just going to be method of undetermined coefficients. We're just not calling it that necessarily until we get to probably here. Mook. And at this point, you're just labeling it because we've been doing it, so like we don't need to do anything other than just say, hey, by the way, this is what this is. Okay, so method of undetermined coefficients is there. Alright, is there anything that I would like to talk about in here besides that? Just that it exists. Okay, variation of parameters. Right, reduction of order is also one. I think doing variation of parameters actually like is slightly better described in terms of matrix interactions, but I could be just wrong. Oh, wait. Reduction of order finds homogeneous solution, doesn't it? Let's see. Yeah. Well, that's a different book. Nope. Nope, 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 nope. Nope. I mean, really, I should just look it up on here. 'Cause excuse me. Okay, yeah. Reduction of orders for finding a second solution. Alright. So reduction of order gets moved up. Got particular solution methods. This also means that for matrix stuff, this is also not just going to be it, because we also have shortened form. There's a bunch of stuff in here. Huh. Oh, there we go. 140. that's right. Matrices aren't really a thing when this book came out. Like, mathematicians have been working with it, but this is 1946. So, like, linear algebra was in its infancy. Still at that point. Alright, so Jordan form diagonalization. Duplicated ones. And when you start talking about it in terms of matrix form, things get a little bit weird, but okay. This also involves the Wronskian at this point. Could be wrong. It's been a while. No, not really. Particular solution. Matrices 254 is the furthest along. Oop, I doggered a page. Laplace transforms. Not a thing. Okay. Okay. I think we're probably going to call it a night because it's just about 12:30 here, local. And, yeah, we're starting to fade here. But this is a good extension onto what we had before. Zach, we'll get back to you on Discord as far as when we're going to continue playing. Good job. I have not played any further than the prior missions that have already been locked, score locked and everything. My kids went further, and I'm like, no, don't look. So they're like, this is hilarious. I'm like, yes, it is. Please don't spoil anything. Alright, so we're going to go and see Danny Anduza, aka Paleontologizing, provided that he's still up here.